Hello, my name is Katie Cronin, and this is my Lab 3 results and my presentation. So here's the basic outline of the presentation and everything like that. And so here are the laboratory objectives and everything, where basically we have an identical circuit to Lab 2 of a Wheatstone bridge and everything to measure displacement and basically the strain gauge and everything like that. And where we would either displace it with our finger, a weight, and then we would see how the damping ratio will be affected by either duct tape or carpet tape and such. And we were basically, again, measuring dynamic tip displacement and everything like that. And then we would then gather all the data to then compare it to the experimental data and then versus the theory and see how close we have it and everything. And then finally, we would do a spectrum analysis for the natural frequencies that we would calculate. And then here's the initial setup and everything, and here's everything labeled. Again, at the very on the left-hand side is the Wheatstone bridge, the clamp, everything like that, and how it's connected to the MSP24 and then to the computer, along with the specifications set in the manual from Lab 3. And yeah, basically on the right-hand side, you see the measurement ruler, and we would use that to see how far down we would displace it or how high up we would drop the weight and everything like that. And then here is a more closer detail of the actual circuits and everything and the Wheatstone bridge. And again, the specifications for the DAQ and such, and how we would have it at 2000 Hertz for a buffer size, and then we would be collecting data for 7.2 seconds per trial. And then here's the strain gauge sensitivity and everything. The sensitivity of the strain gauge can be used to correlate voltage with deflection and everything. And unfortunately, my data from Lab 2 was not very good, and it was completely wrong. And so I'm using data from Dr. Nowinski and everything like that. And so, yeah, I'm very grateful for him. And there's a linear relationship between the voltage output and the tip deflection and everything. And from Dr. Nowinski's data, we see that the sensitivity is approximately 18,200 volts per millimeter and everything. Then here is the beam equivalent stiffness and such. The spring stiffness is needed to connect the applied load to the actual tip displacement. And again, there's a linear relationship and everything like that between the applied load and the tip displacement. And again, the calculated spring stiffness is from Dr. Nowinski and everything, because my data was not nearly correct and I would not be able to do this without him. So I'm very grateful for that. And yeah. And then here is the actual initial displacement and everything, where we would just have it clamped on and everything and displace it by around 20 millimeters. And then we would release it and then start the data acquisition and everything. And for my actual collected experiment, I was able to see that it stayed still for about 0.61 seconds before it started oscillating. And then here we have case one again, and then at the very bottom you see the parameters and everything that we calculated and everything along with the equations that I would use. And you see here that the curve fitting approach was used to find the parameters. And then basically just the process of how we were able to get the graph on the right-hand side and everything. And then here is actual experimental versus theoretical displacements of the beam tip and everything. And at the very bottom is the equation of the displacement of the beam's tip as a function of time using natural frequency, damping ratio, and damping natural frequency and everything. And yeah, basically the model shows the experimental versus measured and everything like that. And then here is the spectrum displacement with a resolution of 2000 Hertz. And we would use the FFT function from MATLAB to basically make the spectrum graph. And basically, as you can see, there's an initial spike in the beginning, and the natural frequency that I calculated does not quite fully reach it. And I do think it's because of discrepancies and everything like that, such as noise or like other things, maybe vibrations and stuff like that. So yeah. And then here for case two, we would actually drop a weight from 6 inches above the end of the free edge, the free tip of the beam. And you can see how in the beginning it was like basically around 0 until the weight was dropped. And then you can see how the beam is then in a free oscillation and everything like that. Here is case 2 again with the beam and everything and the FFT function used from MATLAB. And it's used to make the graph and everything. And you can see that there are 2 spikes. And then you can see where the first, second, third natural frequencies are shown. Unfortunately, again, mine don't quite really hit where they are. And again, I believe that's because of either discrepancies like noise or data acquisition and everything like that and stuff. And then here is, you can actually see where we do the Wheatstone setup, which is very similar to Lab 2 for the vibration control. And basically tape 1 is the carpet tape. I don't know if you can see it very well. The carpet tape was completely white. And then tape 2 was the duct tape, which is case 4 and everything. And you can see the setup and everything like that. And then here are the actual damping ratios from all 3 of the cases of the no tape, carpet tape, and then the duct tape. You can see their graphs at the very bottom and everything and such. And basically from the data collected from the lab, we can see that both of the tape cases have a higher damping ratio than the actual no tape. And then finally, tape 1, which is the carpet tape, has a higher damping ratio than tape 2. And then here is full table of all of the parameters through case 1 through 4, the natural frequency, damping ratio, damping natural frequency, and everything. And you can see that the natural frequencies are similar for case 1 and 2. The damping natural frequencies are similar for case 2, 3, and 4. And then for case 3, which is the carpet tape, it has a higher natural frequency, while case 1 has the lowest natural frequency. And then out of all the cases from the lab, case 3 has the largest difference of damping ratio compared to the rest of the cases. Then here are the conclusions from the graph, from the lab that I conducted and everything. So carpet tape or case 3 has creates the greatest increase of the damping ratio of the beam and such. And then the impulse will cause the beam's vibrations, oscillation to dampen out faster than the actual initial displacement. And then basically the carpet tape dampens the beam vibration the best compared to the actual duct tape. And then for all the cases and their setup and everything, most of the key parameters are usually around the same and stuff. Again, there are discrepancies and everything, which I do recognize and I can see. And then here are my citations. Thank you.